In this video, we'll talk about how to do integration by partial fractions when your denominator has quadratic factors that are irreducible. So first example, in the last video, we saw how to integrate 1 over x squared minus 4 dx. So now let's do 1 over x squared plus 4 dx. And let me just start with a reminder that's important here. Remember, the derivative of arctan of x is 1 over x squared plus 1. That's not quite what we have here, but it's close, right? Because we could factor out a 1/4, and then we have a 1 over x squared over 4 plus 1 dx. You can make this a little nicer. Write this as 1/4 on the outside. And now we have integral 1 over x over 2 squared plus 1 dx. And now we can do a little u substitution where we let u equal x over 2. And then du is 1/2 dx. So we do have a du in here. If we move one of the 1/2s here to be with the dx, then what we have exactly is 1/2 the integral of 1 over u squared plus 1 du, which is 1/2 arctan u plus c, which is 1/2 arctan x over 2 plus c. Okay, same idea exactly. What if instead of this being x squared plus 4, it was x squared plus 9 or x squared plus 100? Well, I won't go through all of the details here. This isn't something you would have to prove. But if you take the integral of x squared plus a squared dx, what you get is 1 over a times arctan x over a plus c. So this is a fact that you should know. You can prove it by going through exactly the same type of argument here, where you pull out your 1 over a squared, you put one of the 1 over a's with the dx, then you do this u substitution with x over a. I'll also point out this is square root of x squared plus a squared squared. So you can also do this integral with a trig sub where x equals a tan theta. So it's not all that surprising that you get an arctan that shows up here. But I won't go through the details of that. So why did I spend all this time talking about this? Well, this tells us how to integrate a bunch of rational functions, the ones where the denominator looks like x squared plus a squared. Okay, so I'm going to pause and erase and then start with another example of integration by partial fractions where we're going to use this fact. Let's look at the integral of 2x squared minus x plus 4 over x cubed plus 4x. What do we do with any integration of a rational function problem? Step 1, check that it is proper. It is. The degree of the numerator is 2, and the degree of the denominator is 3. 2, we're going to factor the denominator. Well, this is not so bad. We have a factor of x, and then we have x squared plus 4, which we know is irreducible. Anything that is x squared plus a positive number has to be irreducible because if you apply the quadratic formula or something, you would see that the roots of that polynomial are imaginary. Okay, so what does the method of partial fractions tell us? So we have 2x squared minus x plus 4 divided by x times x squared plus 4. This is equal here, this is the method of partial fractions, tells us that there exist unique numbers a, b, and c, so that you can write the function on the left as a over x plus bx plus c over x squared plus 4. When you have an irreducible quadratic factor, what happens is over that quadratic factor, you don't just get b over x squared plus 4, you get bx plus c. You have a linear thing in x and a constant term. So this is a key thing to remember. When you have something like x squared plus 4, you need a bx plus c. Okay, how do we find a, b, and c? Well, just like we found a, b, and c in every other example we've done so far. We put everything over a common denominator. So we have a over x times x squared plus 4 over x squared plus 4 plus bx plus c over x squared plus 4 times x over x. So this gives us a x squared plus 4 plus b x squared plus cx over x times x squared plus 4. What does that tell us? We have two rational functions with the same denominator that are equal, so their numerators have to be equal. So we know that 2x squared minus x plus 4 equals, I'm just going to group the x squared terms together. We have an a plus b x squared plus the x terms, which is just a cx, and then the constant terms, which is just a 4a. So for the two expressions here to be equal, the x squared parts need to be equal, the x parts need to be equal, and the constant parts need to be equal. So what we get is three equations in these three variables, and there's a unique solution to them. So I'm going to pause and erase, and then go through the rest of the details of this example. Our goal was to solve for a, b, and c using this expression that 2x squared minus x plus 4 equals a plus bx squared plus cx plus 4a. That gives us three equations. 2 equals a plus b. -1, the -1x equals c. And 4 equals 4a. These equations are quite easy to solve. We see that a equals 1. So if a equals 1, b also equals 1, and c equals -1. So what does that tell us? So that tells us that the integral we want to solve, 2x squared minus x plus 4 over x times x squared plus 4 dx equals the integral of, well, we had 4 over x plus bx plus c, x minus 1 over x squared plus 4 all dx. So we can write this most easily as 4 integral 1 over x dx plus, let's split this part up into the sum of two integrals, x over x squared plus 4 dx minus integral 1 over x squared plus 4 dx. This first term I know, this is 4 natural log absolute value of x plus c. And this last term we know, because we just did it at the beginning of this lecture, is 1/2 arctan x over 2. And we'll get a plus c from the whole thing. So the question is, what about this term in the middle? This term in the middle is actually kind of the easy part. If you set u equal x squared plus 4, then du is 2x dx. So we get as a 1/2. So we get plus 1/2 the integral of 1 over u. So what we get is natural log absolute value x squared plus 4. We actually don't need the absolute value here because x squared plus 4 is always greater than or equal to 0. So our final answer to this sort of long irreducible quadratic factor example is 4 times natural log of absolute value of x plus 1/2 natural log x squared plus 4 minus 1/2 arctan x over 2 plus c. So as you can see, these integration by partial fractions problems, when you have irreducible quadratic factors in your denominator, can really get pretty tricky. So let me pause and then tell you what happens when maybe you have a more complicated denominator that has an irreducible quadratic factor. The last thing I want to talk about in this video is what if you have a more complicated denominator that maybe has more than one irreducible quadratic factor. So let's take the integral of 4x minus 3 over x minus 1, a linear factor, times x squared plus 2 times x squared plus 3. What does the method of partial fractions tell us in this case? It tells us that there exist 5 unique numbers, a, b, c, d, e, with 4x minus 3 over this denominator equals a over x minus 1. We get one term for each distinct linear factor, plus bx plus c over x squared plus 2. Here's an irreducible quadratic factor, and the numerator is some number times x plus some number. And then we have another term that looks like that, dx plus e over x squared plus 3. So I'll just highlight these two and say we get one of these for each irreducible quadratic factor. And again, you should know what the method of partial fractions says here. Like, we could find a way to ask about the form that the method of partial fractions tells you in a true, false, or multiple choice type setting. What we would not ask you to do is find these values of a, b, c, d, and e. You need to put everything over a common denominator, and then you would get 5 equations in these 5 variables. And right now, we just don't have the tools to solve those kinds of equations. You'll learn them when you take Math 3A, but we would not ask you to actually do this integral on a quiz or in an exam. So let me also point out, there are much more complicated looking denominators like this out here. Maybe you have an irreducible quadratic factor squared or cubed or to an even higher power. Maybe you have an irreducible cubic factor. In all of those cases, there is some way to understand how to integrate those rational functions using some kind of partial fractions idea. But we are not going to talk about anything more complicated in this class than your denominator having all linear and quadratic factors. Your quadratic factors can be irreducible, but they're not going to be repeated. You might have repeated linear factors. So we'll see some more examples in the last video where we talk about what to do when you do that first step and you check and see that your rational function is not proper.